Have you ever looked up at the night sky and felt the pull of the stars, that quiet question echoing in your mind, why can't we just go there? The closest star to us, Proxima Centauri, is more than 4 light years away. A light year is the distance light travels in a year, nearly 10 trillion kilometers. That number is almost impossible to imagine, so let's make it concrete. If Earth were a basketball and the Sun were 30 meters away, Proxima Centauri would be nearly 120 kilometers distant. Imagine trying to walk that distance carrying all your food, water, and shelter. That's the scale of interstellar travel. Even our fastest spacecraft, the ones that have left the solar system, would take tens of thousands of years to reach it. The sheer vastness of space is the first barrier, and it is absolute. Space isn't just far, it is incomprehensibly far. Every calculation reminds us that distance is not just a number. It's a physical reality we cannot wish away. The second barrier is energy. Rockets propel themselves by throwing mass backward. It's the simple rule of momentum. Push something in one direction, and you move in the opposite direction. But there is a catch. To go faster, you need exponentially more fuel. It's not linear. To imagine it in human terms, think of trying to walk across a football field. Each step is easy. Now imagine trying to cross an entire continent. You would need food to fuel your steps, and you would need to carry that food, which itself requires energy. If the fuel you need is fuel itself, you enter an exponential spiral that grows so quickly that it becomes physically impossible to carry enough. The rocket equation, the formula physicists use to calculate this, is brutally honest. It doesn't care about ambition or desire, it just tells us the numbers. For interstellar speeds, the vast majority of your spaceship would be fuel. Very little would remain for humans, life support, or anything useful. We are constrained not by imagination, but by the immutable math of motion and mass. The next barrier is speed, the universal speed limit set by Einstein's theory of relativity. Nothing with mass can reach the speed of light. As an object moves faster and faster, its mass effectively increases. The energy required to accelerate it rises toward infinity. Imagine pushing a shopping cart. At first, it is easy. As it becomes heavier, your arms strain more, and at some point no human force is enough to move it faster. The same principle governs spaceships approaching light speed. You can approach it, but never actually touch it. That limit is a law of nature, not an engineering problem. It is a cosmic rule etched into the fabric of reality. Even if we had unlimited energy and somehow neared light speed, the universe itself becomes a hazard. Tiny dust particles, micrometeoroids, and cosmic radiation transform into deadly projectiles at high velocities. What is harmless at slow speeds hits like bullets when you are moving close to the speed of light. Humans are fragile, unshielded against the vastness and violence of space. Long-duration travel exposes us to radiation, zero gravity, and the psychological strain of isolation. Even with technology, the voyage could span generations, meaning those who start the journey may never see the destination. These are the known barriers: distance, energy, the speed limit, and human fragility. They are not impossible to understand, but they're impossible to ignore. Every calculation, every thought experiment reminds us that the universe is structured in a way that resists our desire to simply step from star to star. And yet, in acknowledging these limits, we glimpse something profound about reality itself, that the universe is not only vast and indifferent, but also deeply coherent, following rules that can be understood if we are patient and careful. To understand why traveling to the stars is so difficult, we need to look closely at energy. Rockets work on a simple principle: for every action, there is an equal and opposite reaction. When a rocket expels fuel backward, it moves forward. This is basic physics, yet the simplicity hides a terrifying truth. The faster you want to go, the more fuel you need. And the more fuel you carry, the more fuel you need just to move that fuel. It is a loop that grows exponentially. Imagine you are running a marathon. At the start, you only carry water for yourself, and that is easy. But what if you had to carry enough food and water to sustain you for years? And what if the food and water themselves needed to be carried in containers that added even more weight? Each addition requires even more support. And soon you realize that the majority of your effort is not going toward moving yourself at all, but toward moving the provisions that allow you to move. This is exactly the situation a rocket faces when it tries to reach another star. The fuel is not just energy, it is mass, and mass is heavy. The mathematics of this is captured in the rocket equation, a deceptively simple formula. It tells us the relationship between the speed of a rocket, the exhaust velocity of the fuel, and the ratio of the total mass to the mass of the payload. What it really says is this: if you want to go much faster, your fuel grows disproportionately. For interstellar speeds, the fuel alone could weigh more than any structure we could realistically build. If a spaceship were made for humans to travel to Proxima Centauri, the fuel could easily outweigh the crew, the life support, the living quarters, and everything else combined. Most of the ship would be energy stored in fuel, and humans would become a tiny fraction of the total mass. We can try clever solutions, like staging rockets where fuel is jettisoned in phases, or using energy sources beyond chemical fuel, like nuclear propulsion. These approaches improve efficiency, but they do not eliminate the exponential problem. Every increase in speed requires an even larger increase in energy. Even the most optimistic nuclear rocket concepts still fall orders of magnitude short of what would be required to reach nearby stars in a human lifetime. There is another subtle point. The energy requirements are not just about moving fast, they are about stopping. If a spaceship accelerates toward a star at a significant fraction of the speed of light, it will arrive with enormous kinetic energy. That energy has to be dissipated to avoid smashing into the planet or star at unimaginable speeds. Deceleration requires as much energy as acceleration, meaning the fuel problem doubles. And even if we somehow solve the fuel problem, we are still limited by physics. The universe enforces constraints through the rocket equation, through mass, and through the speed of light. These limits are absolute. They are not technological challenges that clever engineering can overcome. They are fundamental truths about how matter and energy behave. Every calculation reminds us that interstellar travel is not merely difficult, it is constrained by the very fabric of the cosmos. This is a humbling realization. Our dreams of reaching the stars are confronted by the stark mathematics of motion, mass, and energy. The rockets we can build are tiny gestures compared to the vastness of space. Each equation, each thought experiment, reminds us that energy is a currency we cannot stretch infinitely. To move faster, we must spend more. And the universe ensures that the cost grows faster than we might hope. In this constraint, there is both challenge and beauty. The universe does not yield its secrets easily, but in understanding these rules, we come closer to knowing our place within it. Even if we somehow solve the energy problem, the universe imposes another barrier, the speed limit. Nothing with mass can reach the speed of light. This is not just a suggestion, it is a fundamental rule embedded in the structure of reality itself. As an object approaches the speed of light, its mass effectively increases, and the energy required to accelerate it rises toward infinity. No matter how advanced a rocket we could build, we cannot break this cosmic speed limit. To understand why, imagine pushing a shopping cart. At first, it is light and easy to move. As the cart fills with bricks, it becomes heavier, and your arms strain more. Eventually, it becomes so heavy that you cannot move it any faster, no matter how hard you push. The shopping cart is like a spaceship approaching light speed. As it accelerates, the mass grows, and the energy needed to continue accelerating increases beyond any practical supply. The universe enforces this limit, and it is absolute. Even traveling near the speed of light is dangerous. Tiny particles that float harmlessly through space become deadly at high velocities. A grain of dust, a micrometeoroid, or a stray cosmic ray transforms into a projectile with enormous energy. At 90% of the speed of light, a tiny speck of dust striking a spacecraft would hit with the energy of a large bullet. It is not an exaggeration. Space is mostly empty, but the emptiness itself can destroy anything that moves fast enough. A spacecraft traveling near light speed is like a runner in a hailstorm where each drop hits with explosive force. Shielding against this requires technology and materials far beyond what we can currently create, and even then, the hazards multiply with speed. Radiation is another invisible danger. Cosmic rays and high-energy particles are constantly streaming through space. On Earth, our magnetic field and atmosphere shield us from most of this radiation. In deep space, there is no such protection. Prolonged exposure damages DNA, increases cancer risk, and threatens the function of critical systems on a spacecraft. Living humans in deep space for years or decades would face a radiation environment that is deadly without extraordinary protection, which itself adds mass, requiring more fuel, compounding the energy problem. Time is also a factor. At near light speeds, relativistic effects occur. Time slows down for travelers relative to those left on Earth. This might seem like a convenience, a way to survive a long journey, but it also introduces profound isolation. The stars will move, generations will pass at home, and the traveler becomes disconnected from the society they left behind. Even if the physics could be overcome, the human experience imposes constraints that are just as real as fuel or cosmic dust. The universe, in its vastness, is not merely empty space, it is a domain with rules that cannot be bent or ignored. Distance, energy, mass, speed, and the hazards of space combine to create a gauntlet that challenges human imagination. Every step toward another star involves not just engineering, but understanding fundamental laws of physics. The cosmos whispers its limitations, but in doing so, it teaches. It shows us that our aspirations, while noble, are measured against reality itself. This is where the beauty lies. These barriers are not obstacles to crush our hopes, but reminders that the universe operates on principles we can learn. They teach humility, curiosity, and reverence for the laws that govern all matter, energy, and motion. In confronting the speed limit and the dangers of deep space, we are not failing, we are exploring the deepest truths about our universe and our place within it. Understanding these truths brings clarity, even if it also brings the realization that some journeys may always remain beyond our reach. Even if we could build a spacecraft with enough fuel and shield it against cosmic hazards, there remains a barrier that is intimately human, our biology. Humans are creatures adapted to Earth, shaped over millions of years to live within a narrow range of temperature, gravity, and radiation. In space, none of these conditions exist naturally. Prolonged exposure to zero gravity weakens bones and muscles. Astronauts on the International Space Station lose bone mass at a rate of 1% per month and experience muscle atrophy even with rigorous exercise. Imagine this effect multiplied over decades, as would be necessary for interstellar travel. We would arrive at our destination weaker and more fragile than when we began. Radiation is another invisible predator. The high-energy particles that streak through space penetrate even thick spacecraft hulls. On Earth, our atmosphere absorbs most of this radiation, and the magnetic field deflects charged particles. In interstellar space, humans are exposed to cosmic rays that can damage DNA, increase cancer risk, and impair the function of critical organs. Protecting against this radiation requires heavy shielding, which adds mass to the spacecraft, demanding even more fuel, and intensifying the exponential energy problem. The very attempt to survive in space changes the physics of the journey. Psychological factors cannot be ignored. Humans evolved in social groups, with daily interaction in familiar environments. Isolation in the vast emptiness of space for years, possibly decades, poses a mental strain that is difficult to quantify. Solitude, monotony, and the knowledge that home is unimaginably far away could lead to depression, anxiety, or a breakdown in group cohesion. These are not minor inconveniences, they are fundamental barriers. Even if our bodies survive, the human mind may struggle to endure. Generational travel introduces yet another complication. If we send humans on a journey lasting hundreds of years, multiple generations would live and die before reaching the target. This is more than a logistical problem, it is an ethical and biological one. Every life born in transit is subject to the limitations of confinement, limited resources, and the hazards of space. Their entire reality would be the interior of a ship, with only glimpses of the universe beyond reinforced windows. Interstellar travel thus becomes not just a technological challenge, but a profound question about the human experience. Finally, there is the unknown. Physics is incomplete. Concepts like warp drives, wormholes, or manipulation of space-time are proposed in theory, but they require conditions and energies beyond our current understanding or capability. They are not just engineering challenges, they are problems of fundamental physics. We do not know if the universe allows them at all. Every theory is a thought experiment, a way to probe the limits of possibility, but none are practical today. The unknown reminds us that our knowledge is provisional. It shapes our dreams, but it also imposes humility. These biological, psychological, and unknown physical limits together form a web of constraints. They demonstrate that interstellar travel is not just difficult because of distance or energy, but because the universe, human biology, and the laws of physics intersect in ways that are profoundly constraining. Yet, within these limits lies clarity. We are forced to confront reality as it is, not as we wish it to be. And in understanding why we cannot reach the stars easily, we gain insight into what it means to be human, to exist, and to explore curiosity within the boundaries of the cosmos. The barriers themselves become teachers, showing us the fragile, remarkable, and finite nature of life in an infinite universe. After considering distance, energy, speed, hazards, biology, and the limits of our knowledge, it becomes clear that interstellar travel is far more than a technological challenge. It is a mirror held up to the universe, reflecting the boundaries of physics, the fragility of human life, and the astonishing coherence of the cosmos. Each barrier we encounter, from the immensity of space to the relentless speed limit of light, teaches us something fundamental about reality. They are not merely obstacles, they are the language in which the universe speaks, expressing rules that are elegant, unforgiving, and profoundly instructive. Humans have a natural instinct to push boundaries, to explore, to travel beyond what is familiar. But the universe sets boundaries not to frustrate curiosity, but to define what is possible. The vast distances are not just numbers, they are a measure of the scale at which matter, energy, and time operate. The rocket equation does not exist to punish ambition. It describes the immutable relationship between mass and motion. Relativity does not restrict imagination. It reveals the deep connection between space, time, and energy. Even the hazards of cosmic dust and radiation are not merely threats. They are evidence that the universe is real, active, and governed by consistent principles. In confronting these limits, we are forced into a kind of intellectual humility. We realize that our species, magnificent as we are in ingenuity and curiosity, exists on a small planet, in a tiny corner of a vast galaxy, surrounded by forces we can understand but cannot control. This recognition is not despairing, it is clarifying. It is a reminder that curiosity does not require conquest. Understanding does not require physical presence. By studying the cosmos, by calculating trajectories, considering energy, and simulating voyages we may never take, we participate in the universe without leaving our solar system. Knowledge itself becomes a form of travel, one that is unrestricted by mass, speed, or fragility. Yet there is beauty in the impossibility. The very fact that we cannot easily travel to the stars makes the universe more magnificent. It is vast, dangerous, and intricate, and our place within it is precarious and precious. Every boundary we encounter is a proof of coherence. The same rules that prevent interstellar flight are the rules that allow planets to orbit stars, galaxies to form, and life to emerge. Our limitations highlight the extraordinary conditions that make our existence possible, and they invite reflection on the delicate balance that sustains us. Perhaps the most profound realization is that understanding the limits of interstellar travel changes how we see reality itself. Space is not simply empty. It is structured, ordered, and ruled by principles that we can perceive through observation and thought. Humanity's ambition is bounded not by lack of imagination, but by truth. There is a kind of elegance in that. To explore the universe is to engage with reality as it is, to measure, calculate, and imagine within constraints that are universal. We come to see that the cosmos is not an adversary to be conquered, but a teacher to be understood. The stars may remain physically unreachable, but in learning their distances, energies, and hazards, we touch them intellectually. In understanding the boundaries of space and time, we gain insight into the limits and possibilities of life itself. Interstellar travel may be impossible in practice, but the journey toward understanding is always available, always infinite. And in that pursuit, we discover a truth more profound than motion across light years. The universe is vast, we are finite, and yet, through curiosity and reason, we are part of its unfolding story. Even as we reflect on the barriers of energy, distance, speed, and biology, there remains a deeper layer to the problem, the unknown. Physics is not complete. Our understanding of the universe is based on observation, experimentation, and the equations we have discovered so far. But there may be phenomena beyond our comprehension, laws of nature we have yet to encounter, or principles that challenge what we consider absolute. We do not know if concepts like wormholes, warp drives, or manipulating space-time are possible in principle, or if they are forever relegated to the realm of thought experiments. We can speculate, calculate, and theorize, but the universe has the final say. This uncertainty is both a limitation and an invitation. The impossibility we face is not merely a wall, it is a doorway to curiosity. It forces us to confront the question, what does it mean to reach for the stars when physical travel may be unattainable? Perhaps reaching the stars is not a question of moving through space, but of expanding the mind, extending knowledge, and understanding the laws that govern everything from the tiniest particle to the largest galaxy. The human ability to imagine, to reason, and to calculate trajectories we may never fly along is itself a form of exploration. Our perspective is shaped by scale. We're used to distances, speeds, and lifespans that are familiar on Earth. A few kilometers, a few hours, a few decades, these are intuitive. But interstellar travel forces us into scales that are alien. Time stretches, energy requirements explode, and even the concept of life itself becomes relative. The universe does not bend to human experience. We must bend our thinking to its reality. This is why space is so humbling. It reveals that human intuition is limited, that our desires do not dictate possibility, and that the cosmos operates according to principles far larger than our everyday lives can contain. Yet there is a kind of freedom in these limits. They define a universe that is orderly, comprehensible, and consistent. Every law we uncover, from the rocket equation to relativity, allows us to make predictions, to understand why things happen, and to see the consequences of action and inaction. Knowing that we cannot reach a distant star in a human lifetime does not diminish its wonder. It sharpens our appreciation for the complexity and coherence of the cosmos. The boundaries become a framework for exploration, a lens through which we can study the universe with honesty and precision. In this reflection, we begin to see a paradox. The closer we approach the impossibility of interstellar flight, the more we understand the universe and our place within it. Our constraints do not isolate us. They connect us to the deep structure of reality. We are participants in a system governed by immutable laws, capable of understanding those laws, and able to engage with the cosmos intellectually even when physically confined to a small corner of space. The limits of travel, then, are not failures. They are proofs of coherence, guides to wisdom, and catalysts for imagination. Ultimately, the physics barriers to interstellar flight do more than define what we cannot do. They illuminate what it means to exist within a universe that is vast, elegant, and unforgiving. They compel us to see life, thought, and discovery as intertwined with the fabric of reality itself. And they remind us that while the stars may remain unreachable, the journey of understanding them is infinite, eternal, and profoundly human.